Welcome as we entertain moving to the second part of the semester in business statistics. And in the second part, we'll start off with learning a bit more about sampling, the nature of sampling. We're going to learn how to develop a plan, a sampling plan. What are we talking about when we're talking about confidence intervals? When we're looking for a mean, when we're looking for a population of a total census versus a sample. Population intervals, when the population standard is the population standard deviation is unknown. And then we're going to look at what should we use as a sample size when we want to deal with a certain level of confidence or a certain level of probability that the mean will be found within that level of confidence. We've talked about this statistical inference chart multiple times, but this again is just a picture of what we're looking at. We're taking a sample out of a total population, out of a total census. From that, we're inferring that the data we pulled from the sample is going to be equal to or very close to the total population. So we've talked about statistical inference. It's the process of reaching a conclusion about the characteristics of an entire population from data from a subset, or as we referred to before, a sample of the total population. The inference, then we're trying to connect the sample to the population. With proper sampling methods, the sample statistics will provide good estimates, and I emphasize good, of the total population parameters. So why do we do a sample? And I think I'd like to recommend you look at this slide a little bit more because this is a quiz question. Why do we sample? To reduce cost, reduce time and effort, most common reasons. Other example, if we're doing destructive testing on a product, if we're in the testing process, we very well can't do it to the entire population. We better do a sample. And then when the evaluation of population members is highly technical or tedious, sampling may produce better results than a total census. Choosing a sample size. One of the first things we have to decide is how many. How many do we want to sample? We choose too few, we risk relying on an insufficient representation of the total population. If we choose too many, we defeat the purpose of the sampling. So let's use small n to represent the sample size and big N to represent the population size. This again is consistent with where we've been in the past. So we need to do some random sampling. What do we mean by random sampling? Sampling method which ensures every combination of small n members of the population has an equal chance of being selected. Random and equal opportunity being key words here. Let's look at an example. Dean of Students at a High Plains College is planning a study to assess how the 1,000 members of the freshman class are adapting to the academic rigors of college life after the first month of classes. Among other things, she intends to determine the average study time for the students for the first year students. Keep in mind, my note here, this is not inclusive of the time that's expected to be included in posting to discussion boards. There are two alternatives to determine the information we're looking for. Number one, we can do a total sample. Total consensus. We can look at the population. Conduct a census of the entire population, all 1,000 people. We already know how we're going to do the population mean and the population standard deviation. We've learned that in chapters 4, 5, and 6. Alternative 2, we can take a random sample of n from the population. We're going to let n equal 40 in this case. You can use the random number generator on 234 of your text. All of the digits are represented equally, so there's no way to be inconsistent in our process. We can use with or without replacement. We've talked about that a little bit, the concept of it anyway, when we talked about the deck of cards and how often are we going to pull an ace of spades out. What's the chances of getting a second ace if you pull an ace out the first time, with and without replacing the card back into the deck? So going back to High Plains College, we want sample mean will be used as a point estimate, and that's a new term now, of mean. The average study time last week for the population of High Plains freshmen was, they must not have had any statistics classes that they were attending, because they've only put 18.6 hours in as a mean. Different random numbers would have identified a different sample, which would have resulted in a different point estimate. So in other words, of that 1,000 people, we've selected 40. If we selected a different 40, we would have gotten potentially different numbers. So what's the confidence interval? How does knowing the sample mean enable us to know the mean of the entire population? A couple of interesting questions. Would you expect the population mean to be exactly the same as the sample mean? Absolutely not. Not very likely would that happen. Should we expect it to be similar to or in the neighborhood of a sample mean? Absolutely. That's what we're looking for. Closeness. And now how close do we need it to be? What's acceptable? How much confidence do we need in our numbers? We use the table from the sample to produce a sample stat that serves as an estimate of the population. When the point estimator, X bar now, of the population, we refer to that, and then the standard population, standard deviation, or S in this case, is now the point estimator. A couple of different terms is all. Interval estimate, rather than settle for a point estimate likely to be wrong, we're going to construct an interval estimate. In other words, the point estimate plus or minus some amount is going to be our mean of the population. We call this a confidence interval since we'll be able to attach a level of confidence or probability or chance that the interval will contain the mean. The notion of sampling distribution is the single most important idea in all of statistics. Sampling distribution of the sample mean. What does this mean? So what are the chances, what are the probability of all values of the sample mean when a sample size of some quantity is taken from the total population? What are the chances that it's going to fall within that distribution? We've talked about the old bell-shaped curve a number of times. So properties of the sampling distribution of the sampling mean. What does that mean? For large enough samples, the shape of the sampling distribution will be approximately normal. If the sampling size is large enough, it's going to look like that old bell-shaped curve. The sampling distribution is centered on the mean of the population. shape of that distribution when the sample size is equal to or greater than 30. That's a key number, equal to or greater than 30. Back to that old central limit theorem. As sample size increases, the sampling distribution of the sample mean rapidly approaches the bell shape of a normal distribution, regardless of the shape of the parent population. Keeping in mind a sample size of 30 or equal to or greater than 30 is considered large. If the sample size is less than 30, the sampling distribution of the mean will be normal as long as the parent population is normal. Mean and the standard deviation of the sampling distribution of the sample mean. What's the expected value? And we did that last chapter. How do we calculate that? Then, what's the error rate? What's the standard error of the mean? In other words, in the sampling distribution of the sample mean, how much variation, how much distribution are we looking at? Again, just the formula to calculate that. The standard deviation of the sample mean is the standard deviation divided by the square root of the sample size. So, now some new terms again. Interval estimate of the population mean. I've only got a sample that I'm going to be looking at. What are the chances that that sample is going to look like the total population? So the interval estimate of the population mean is as identified here. Keeping in mind, we have a new item in the formula here. It says Z. And if you remember correctly, going back to your distribution tables in the back of the book, if we recall, we wanted a high 95% confidence level was one of them. And if I remember correctly, 95% confidence level equals a z-score of 1.96. So we look on the tables and see that 1.96 equates to a 95%. Divide that by 2. That gives us 0.025. We plug that into the formula, and the rest of the numbers we've gotten, the standard deviation and the sample size, the square root of that, and that's going to give us a confidence level. Somewhere between the two lines here is where the mean is going to be for the population. So we've now we've built a confidence interval for the population from our sample size. So what influences the population width? What happens if the sample size, and knowing that that'll always produce a tighter interval? If we recall back, we looked at one standard deviation on either side of the mean, included 68.3% of the population means. If we look at two standard deviations on either side of the mean, we were looking at 95.5%. And when we looked at three standard deviations, we were at 99.7%. So at that point, anything outside of that, if you recall, we considered an outlier anyway. So sampling error. The difference between a point estimate and the corresponding population parameter is called sampling error. X bar minus the mean. Totaling those. This is the way we did that before, if you recall. So we've got what we have is a standard error, and then we have a margin of error. Two formulas. How do we get the margin of error? What does margin of error mean? Now we're referring to that 95%, 98.3%, I think was the other number, 99.7, 68.3%. How many standard deviations on either side of the mean are we looking at for margin of error? What's acceptable to us? An example. Starting salaries of doctors. Starting salary for the sample of 200 people was 78.4. Using this result to construct a 95% confidence level, that's what, 1.96, right? Z-score. Estimate of the mean for the population of all newly hired physician care units, physicians in the U.S. Assume standard deviation to be $5,500. So, problem statement, 95% probability, or possibility, I guess I should say probability, that a randomly produced sample mean starting salary will be within $762.25 of the population mean as we go through the formula here. 95%, when we go to our tables, comes out to 5%. Half of that is 0.025. So we've got the formula we worked out, and we got $762 on either side of our mean. So we add the 78.4, we add 762.25 to it, and we subtract 762 from it. So we can say that within 95% confidence that the interval for the population will be between $77,600 and $79,162. So what if there's no population standard deviation known? What do we do? Now we're going to start, and we're still referring to the sample standard deviation as S. Now we're going to go to the t distributions. We're going to grow our allowable deviation to grow a little bit here. We're going to go to t tables. So what is a t table? Remembering we're trying to estimate the population standard deviation based on a sample standard deviation. So the calculation of the sample standard deviation involves the denominator of n minus 1 instead of n, and that's going to increase our degrees of freedom, we're going to refer to it as. If we think of our sample size as n, and we're going to subtract from it, if it was 28, we're now going to call it 25, and we're going to look at what's the degrees of dispersion that's allowable with the new degrees of freedom.